Hi everyone, I want to go over the homeworks from 8.3, that is solving equations using Laplace transform, and so the first one that I signed was number 21. Now that, I admit this is a very tricky one, it took me a little while I had to think about it too. It's not a straightforward one, so it's a tricky solution. So be forewarned, it's going to be a little bit of trickery. And therefore I will not ask you to do something like this. But each of this, it's actually a combination of two tricks. But each of the tricks separately you should know. But the combination of the two tricks, that is perhaps a little bit too much to ask. I mean, as I said, it took me a little while to figure this out. So here is the differential equation that we're talking about. Okay, and the initial values are y0 is 1 and y prime of 0 is -3. Now let's start with the formulas. So what are the two formulas that we're going to use? We're going to use Laplace transforms. So we need to know what the Laplace transform of a derivative is. And that is the Laplace is s times the Laplace transform of the original one minus y0. And if we do the Laplace transform of the double derivative, that is s square lambda, the Laplace transform of y minus s times y0 minus y primes 0. Okay, and the way that we're going to do is we're going to apply Laplace transform to both sides, and we're going to write this in terms of the Laplace transform of y. So we introduce that also as our new variable. This is going to be y. When we write little y, we think of y as a function, but we think of it as a variable, a function that we don't know yet. So we're solving for that function. And this is the same here, but capital Y is just going to be the Laplace transform of this guy. Now, it's perhaps sometimes easier to remember these formulas if you introduce this y here, because then this is just sy minus y0, and this is s square y minus sy0 minus y prime 0. Okay, so in our case, we have y double prime. Okay, so right. So let's apply the Laplace. So we give this plus lambda, Laplace of y equals the Laplace of t minus 3 times the Laplace of sine 2t. Okay, my Laplace was a bit crooked here. So 3 times the Laplace of this one. And here we're using here, of course, that Laplace transform is linear, that we can move it through sums and constant multiples. Okay, so this one is s squared y minus sy0, but that's 1, so minus s, and then minus y prime 0, that is minus 3, that is plus 3. And this is just y, right? This one. So this one is what the first one. Now, these guys, well, those we have to calculate. And so we know that very quickly, right? We know that a power, Laplace transform, it goes into a power with a higher exponent n in the denominator and an n factorial on top. Okay, and then the sine 2t and omega t and cosine omega t, they convert to something of the form. The sine is omega over s squared plus omega squared, and this is s over s squared plus omega squared. Okay, so here the t therefore becomes 1 over s squared, and this becomes minus 3, and there's no shifts here, no exponentials. Exponentials, remember, cause shifts, but there are no exponentials, so there are no shifts. So this would now be minus 3, and omega is 2 in this case, right? So this is omega 2, so we get a 2 on top here, don't forget there's an omega there, s squared plus 4. Okay. Sorry. Just quickly double checking that I didn't copy anything wrong. Okay. So now we have to 1 over s squared. I said square, but I wrote 1 over s, right? Because this is power 1, so this will be power 2. Okay. And here we will get 1 factorial, which is just 1. Okay, this is now an equation in y, but a very simple one. A linear equation in capital Y, so we solve for capital Y. So we get s squared plus 1, capital Y, is equal equal to, now I bring these two guys to the right hand side, s minus 3 plus 1 over s squared minus 6 over s squared plus 4. And now we have to divide, solve for y here. Now, you might be tempted to put everything on common denominator, but let's think about, before we continue, because I said it's tricky, right? And the tricky part is here. Suppose I would have given you this in a previous session, in chapter 5. We know what to do in this thing, because this is constant coefficient, so the homogeneous solution is very easy to write down. And if you think quickly, t squared plus 1, so imaginaries, right? Omega is 1, so it's cosine and sine, right? Okay. But what do we do here? Each of these we can deal with, because we know how to deal with sines and cosines. We discussed this not in chapter 5, but in chapter 6 when we talked about harmonic equations. We showed how to do that. We also, in chapter 5 itself, we did check how to do this, guys. In fact, we could do a polynomial, an exponential times a polynomial. This is a very simple case of that. And what do we do then if we had two of those? So that might be something you have to think a little bit about it, but it's important to remember this. This is an important technique. This is the technique of superposition. So what you would do is you would look at two different differential equations. You would look at the one where you only look at the first one, and then this one where you ignore this t and solve this one. So you would get two differential equations that you find a particular solution for, and if you add the two particular solutions, that would be the particular solution of the whole thing. Okay? So you would work this separately and this separately. Now, in this method, we're treating both at the same time, but we should, I'm not saying it right, so because we have now several terms, we should be a bit careful to combine them too quickly. So what I'm going to do before I'm deciding on common denominators, let's just solve for y, okay? This means I have to divide both sides by s squared plus 1, and if I have a sum, I'm going to divide each of these by s squared plus 1. So let's see what we have. We get s minus 3 divided by s squared plus 1 plus 1 over s squared plus 1 s squared minus 6 s squared plus 4. S squared plus 1 here, right? S squared plus 1 times s squared plus 4, sorry. We're dividing everything by s squared plus 1. And what is the next step? Before we analyze it, let's think what we need to do. Well, we know that y is the Laplace of little y, so we're going to do the inverse Laplace, and we will get little y. So we need to do the inverse Laplace of this guy. Now, this is a rational function, so what we do is we find the partial fraction of that. But before you start just diving in, let's see what we have already. This is a partial fraction. This term on itself is a partial fraction, so there's no need to do anything with this one. So that is the tricky part. That's the trick that I said. The trick is that you do not use this. That you do not touch this. This is, we know what what is the inverse Laplace of this one? Well, we know I have to split it. This one will give me the cosine. This will give me some sine. Okay, I have to think about the coefficients, but that's what it is. Okay, so it's only these two I have to deal with. I have to put those, I have to find the partial fractions of these. Now, we can do each separately, but in this particular case, you can even do both together. And perhaps that is harder to do them both together, but it is quicker. So I'm going to show you how to do these two together. Of course, if I mean to do it together, it means I have to put them on common denominator. Okay? But it might be better, perhaps, for you to do it each separately. So find the partial of this, find the partial of that. Now, you still would protest and say, but Professor, this is horrible, because, I mean, even this is the worst one of all, because it's two quadratic irreducible. So we have an A, a B, a C, and a D, but there's no roots, so we have to put, this is going to be a big linear system of equations that we have to solve, and we have to do it not once, but twice, because this is not much better. There is only one root. This root is a multiplicity 2. So again, a lot of calculation. So the calculations to find A, B, C, and A, B, the partial fractions of each of these could be very lengthy if you just do it straightforwardly. And now you're going to combine this. That's madness. But no, I'll show you how combining them doesn't make it easier, but it doesn't make it harder either. That's my point. So bear with me. I'm going to combine them, so I have to put them on common denominator. So for the moment, so let me perhaps box this a little bit. For the moment, I'm going to only work with these two. Okay, so this the first one I'm not touching because it is in the form that I want it to be. Okay, so what do I do with this? Well, I have to put this on common denominator, which would be s squared plus 1, s squared plus 4. Now, what is missing here? Well, there's an s squared plus 4 missing. Okay, minus 6, and what is missing here? An s squared. Okay, so I can combine this. This would be minus 5s squared plus 4 over s squared plus 1, s squared plus 4. Professor, what are you doing? Now, the partial fraction, how would it look like? There's an s in the denominator, an s squared in the denominator. Then there's s squared plus 1 with a linear polynomial on top, and another one with linear polynomial. We're talking about 6 coefficients. Wouldn't it be better to do just 4? That was already horrible, but here's the trick now. Notice that this whole thing is in terms of s squared. That's the beauty of this. This whole thing is in terms of s squared. So that if I do the substitution, z equals s squared, what does this become? This becomes minus 5z plus 4, z plus 1, z plus 4. Look at that. Now you want to do the partial fraction, right? Now you're saying, oh, let me do it because I know how to do this. Because we have different roots, we can use Heaviside. So we're going to get this very quickly. Okay, I should write it here because I need my space. So, because we know how it looks like, right? Right, it's going to look like S as what? Well, it's going to be an A over Z plus B over Z plus 1 plus C over Z plus 4. And how do you find it? Well, okay, I'll do it here on the side again. You take this fraction. And then for A, since A is on top of Z, we scratch out that Z and plug in Z equals 0. That is, therefore, we get 4 on top, and in the bottom I get 1 times 4, 4, so A is 1. Okay, so and again, here I'm going to do my little cheating, put a 1 here, and now I'll do the same for B. So I'm going to calculate B here. So what is B? Now, in B, is on top of z plus 1. So that factor goes, and what I plug in? 1? No, negative 1, right? It's the one that makes that factor 0. So if I plug that in, I get a minus that is plus. So 5 plus 4, that is 9 on top. And in the bottom, I get a minus 1 times 3. So I get minus 3. That's B. Okay, that's good, that's good. And then finally the C, what do we do with C? Same thing. So for C, now this time it's the factor, oh, I forgot to erase this one. It's the factor Z plus 4 that should go, right? This guy has to go, and I have to plug in Z equals to negative 4. And that is then equal to, negative 5 times negative 4 is 20, plus 4 is 24. And in the bottom I get minus 4 times minus 3, yeah. So this is actually 2, right? It is 12, 24 divided by 12 is 2. So that is C. And now we can plug back in what Z was. Z was S squared. It's 1 over S squared minus 3 over S squared plus 1 plus 2 S squared plus 4. Okay? Now, don't forget, we now go back to what we have. So y is, we also have this guy here still, right? Which, let's split it already, because we know we have to split it. S over S squared plus 1 minus 3 S squared plus 1 plus 1 over S squared minus 3 S squared plus 1 plus 2 S squared plus 4. Now, there's one, this is S squared plus 1, right? These two can be combined into minus 6, right? So this would be minus 6, and okay, so combine them. And so now each of these are inverse Laplace, can be read off from the table, right? This is just cosine t. There's no shift, and omega is 1 here. Okay. The next one is a sine, but okay, remember for the sine we had an omega on top here, so we have to divide here by. But omega is 1, so there's nothing to divide by. So this is minus 6 sine t. Okay. What about this one? Cosine, sine, omega is 0. No, that doesn't make sense. This is different, right? Don't confuse. This is a power of s in the denominator that corresponds to powers of t. And which power? Well, 1 less. There we go. And then the final guy, what is this? Well, now omega is 2 here, right? And this is a sine. So this is just sine 2t. And this is the solution. I think the back of the book has a slightly different, I think they made to me it looks like a typo. Let me double check here. Was it this one? T minus 60. Oh, no, they have the same thing. No, okay, that's the solution. So here the trick was, this is a double trick. The trick is that if you have and this is a trick, this is a morale, a lesson, right? If part of it is already a partial fraction, remember what that means. That means that the denominator is either quadratic irreducible or a power of s plus something squared, like a variable squared. With a variable, I mean a shift of s, right? And on top, we have something of lower degree. That's also important, right? And top we have here, if it's these guys, we have to have constant on top of it, okay? But so this is a partial fraction. These are not. So we have to make this into partial fractions. But if you have already one, there's no need to put it all together in the big guy, right? Just do the separate. And I said, how do you do these two separately now? Well, you do the same trick that I used here, because again, these each depend only on a square. So you can do this here. So this would be 1 over z plus 1 times z, and this would be minus 6 z plus 1 z plus 4, which is very quickly done, and it would be, you have to do heavy side twice instead of me doing it. Well, 2 times twice, twice 2 times, and here I did once 3 times. Up to you to decide what is quicker. Okay, so